So number 1 is 25 to the x equals 5. Number 2, 3 to the m equals 81. Number 3, log base 4 of 64 equals x. Number 4, log base 1/2 of 4 equals m. Number 5, 1.904. 5 through 8, I would require work because I'm asking you to use these two things, so you would have to show me the work to show me how you use those two things. So if all you had was the answer on those, you wouldn't get your points. 6 is 0.544, 7, 1.748, 8, 1.204. Number 9, 1.4404, 10, 0.6644, 11, 3.3476, 12, 1,928.7527. Sorry, I obviously made up that problem. It was not pretty. 13, 3, and 4. 14, you could have it as a radical, -1 plus or minus radical 3 over 2, or the decimals 0.366 and -1.366. 15 is -16 over 9. 16, 21.1331. 17, -1/2. 18, -0.2984. 19 is 4. 20, 9/2 or 4.5. 21A is, it took 15.327 years, or you could say during the year 1965. B, it took 24.926 years, so that's during 1974. 22, 16.6164 years. 23, it is not 1-to-1, so that means it doesn't have an inverse. 24, your inverse is 1 minus 2x over x. Domain of the function and range of the inverse are -infinity to -2, union -2 to infinity. Range of the function and domain of the inverse, -infinity to 0, union 0 to infinity. 25, your inverse turns out to be the exact same as your original function. So the domain and range of everything is the same, -infinity to 1, union 1 to infinity. 26, your graphs, I would expect a minimum of 3 exact points on those. So 2 to the x is just your increasing, 1/2 to the x is decreasing, log base 2, and log base 1/2. Looks like that. Number 27, I would say you had to show work on the test for that, so you have to show the change base formula, so that's 2.1534. 28, expanding, so 2 log base 5x plus 5 log base 5 of y plus 1/2 log base 5 of z minus 4 log base 5 of a minus 7 log base 5 of p. And 29, you condense it. You have 1 log out in front, y to the 5th, x minus 1 cubed, over x times x plus 3 to the 4th. Oh, yeah, I added a question on yours and I forgot. All right, so let's talk about questions 5 and 6. 5 through 8, I was really just trying to get you to use your properties of logs. So I may not ask something specifically like this on the test where, I give you a couple decimals and say to evaluate these things, but I may ask you questions involving these properties. So that's where I was going with those on the review. Number 5, you can probably expect me to ask this one somewhere. What would we need to do? Change of base. There was another change of base question on here, and I told you when you do that, you have to show the work. So that's log of the argument divided by log of the current base. And then in the problem, I gave you the decimals that I wanted you to use for each of these. So log of 14, I said, was 1.146. Log of 4 was 0.602. So you divide those and you get 1.904. So I'm really just trying to get you to remember all of the properties that we've had. For 6, we had log of 14 divided by 4. If you have a log of things being divided, how do you break it up?
Subtract.
So that's the log of 14 minus the log of 4. So log of 14 is 1.146 minus log of 4 was 0.602. If you subtract those decimals, you get 0.544. Is that one okay? Number 7, we haven't specifically asked about it, but we're doing the rest of those, so we might as well. How could you rewrite 56?
Log 4 plus log 15.
Right, 56 is 4 times 14. So to break those apart, you add the logs. So log of 4 is 0.602. Log of 14, 1.146. So if we add those, we get 1.748. Number 8, we have log of 16. There are 2 options for that. How do you want to rewrite 16?
4 squared.
Okay.
You have to move that 2 over.
Right. You can do it as 4 squared or 4 times 2. Or sorry, 4 times 4. Properties of logs, if you have an exponent, that comes down in front. So that is 2 times the log of 4, which is 0.602. And if you multiply those, you get 1.204. All right, are we okay with those? All right, next question we asked about was number 13. And if we have time, we'll come back to some of these others. So number 13, was there one specific? Sorry. We have log of 7x minus 12 equals 2 log x. So once we got into these log problems, we had to think about our strategies. We had to first look, is there more than one log? So we see we do have logs on both sides. There are no terms without a log. So our strategy is going to be just to get a log of something on each side, and then we can drop those logs. So what would we do with that 2? So now we have that log on each side, so we can drop it. So 7x minus 12 equals x squared. It's a quadratic, so we always want to set these equal to 0. I want my square term to be positive, so I'm going to subtract over my 7x and add over my 12. All right. From here, what do we do?
You can do just, you can back.
Mm-hmm.
That x minus 3 and x minus 4.
Right, multiply to positive 12, add to negative 7, so negative 4, negative 3. Set each of those equal to 0, so you get x equals 4 and x equals 3. What do we have to remember to do on every log problem?
Check, check.
Check it. The argument has to be positive once you plug it in. So if I do that, 7 times 4 minus 12 is positive, 4 is positive, 7 times 3 minus 12 is positive, so both of these answers work here. Right. We have number 20. Do I have any terms without a log? No. When we do, that's when we try to use the definition to go into exponential form. Since everything has a log, my goal will be get 1 log on each side, then we can drop it. So on the left, we have 2 logs subtracted. So how do we put those together? Divide. So that is the natural log of x minus 1 divided by x plus 6. Over here, we have the natural log x minus 2 divided by x plus 3. Alright, so far so good, just using those properties there. So then, we have one log on each side, so we can drop that. What happens now? Right, we don't have logs anymore, we just have a fraction equal to a fraction. So we can cross multiply. So if I do that, we have to FOIL. X minus 1 times x plus 3 would give me x squared plus 3x and minus x is plus 2x minus 3. And if I multiply these, we get x squared minus 2x and plus 6x is plus 4x minus 12. So if I subtract over my x squared, lucky for us, those cancel. So we really just have a linear function. So we can get all of our x's together. So if I subtract it over my 4x and add over my 3, and negative 2x equals negative 9, divide by negative 2, so x equals 9 over 2, or 4.5. We have to check, make sure when you plug that in, 4.5 minus 1 plus 6 minus 2 plus 3, all of those are positive, so it's okay.
So, after we cross multiply, we just add an
Think about cross multiplying. Alright, let's say I gave you this. If you wanted to get rid of the fractions, first you would multiply over this 4. Right? So you have 20 over x equals x plus 1. And then you would come back and you would multiply the x, which is really what happens if you just cross multiply. So you're just left with an equal sign in between. Next up, we have problem 21. Alright, so I told you this equation was measuring our population. And part A asks how long until it has doubled. How many people did this town start with? 500. So if it doubled, how many people do we have? So we're just solving, so subtract over your 500. So then, what do I need to do? Add a log to each side. The benefit of that log is then the t comes down. So then you can divide by log 1.5. So if you plug that in, you get 15.327 years. Or you could have said this town started in 1950, so 15 years later it's 1965 now, when it has doubled. Part B is the same, you're just setting it equal to 25,000 instead. Alright. Problem 23. Okay, so I want to know if this is one-to-one. There are two different ways of doing that. You can do it by looking at a graph or algebraically. On the study guide, I asked you to do it algebraically just so you would refresh that strategy. On the test, I will probably just ask this question and say, is it one-to-one? Justify your answer. So whether you show me the work, or if you look at a graph, sketch me a picture of the graph, one or the other. I won't make you do both. So algebraically, 1 to 1 means y doesn't repeat, and we needed that to have an inverse. So what we did is we pretended y did repeat. We plugged in two different values for x. We just used a and b typically, and set those equal to each other. So what that's saying is these y's are equal. If you solve this and get a equals b, that means the only way the y can be the same is if your x's were the same. If you get anything else, that means it's not 1 to 1. So I can add over my 6. Then what would you do? Divide by 2. So I get a plus 1 squared equals b plus 1 squared. What would I do now? And when you add a square root, you need plus and minus. And that right there shows me it is not 1 to 1 because I had a positive and negative. So basically we talked about when we did this that anytime it has a square in it, it's not going to be 1 to 1. For that reason, when you solve it, you would have to add a plus and minus. We also think about the graph, the other way of deciding 1 to 1. If we graph this, it's a quadratic. You can use your graphing calculator. It's a quadratic. It looks something like this. No, it doesn't. I moved it the wrong direction. Try that again. It looks something like this. So, is that 1 to 1? No. The reason is it fails the horizontal line test. You can draw a horizontal line that hits that graph more than once. So it is not 1 to 1. Yes, sir.
That wouldn't you be able to tell like just by if the x would be in like absolute value large or if it's squared?
Yep. Those were the things that we talked about that made it not 1 to 1. So if I put that on the test, you could say no because it has a square in it or something like that, and that would be fine too. All right. Is that one all right? The next question was 24. Finding the inverse. So you will have to do this on your test. What would be the first step?
Change over x to y.
So we get y equals 1 over x plus 2. And then what do we have to do?
Change x to 1.
So x equals 1 over y plus 2. Now, we want to get it back in function notation, so we have to solve for y. So we multiply by the y plus 2. So we get xy plus 2x equals 1. Subtract over the 2x. And then what do we do?
Divide by
So we get y equals 1 minus 2x over x. And we usually ended it, instead of y, we would write f inverse of x. I did ask you on this to graph the function and its inverse. You can just use your graphing calculator for that. I'm not going to spend a lot of time talking about that graph piece. That's kind of from the last chapter. Really, the reason I had you graphing them was to kind of help you answer your domain and range question as well.
For that, I was wondering, why wouldn't you do like the x and parentheses y plus 2? Like separate the x into both.
So you're saying right here, keep it as x times this,
Yeah.
and then divide by x, and then subtract your 2.
Yeah.
That's equivalent, and so that's also okay.
Oh.
You'll get, those are equal to each other. But the big thing, so I'm not going to spend the time going over the graph because you could graph it on your calculator, but I want to talk about the domain and range. We know the domain of the function is always equal to the range of the inverse. And we can find that easily by just looking at the original. If you have a fraction, you know what can't happen.
There can't be 0
So my x can't be
negative
-2. So it could be everything smaller than -2, union everything bigger than -2. The range of the function is equal to the domain in the inverse. So if I look at my inverse, what can x not be?
2.
0. So that one will be negative infinity to 0, union 0 to infinity. What if you did this and you didn't have any fractions or square roots? What would your domain and range be? Negative infinity to positive infinity. And we had that happen plenty of times when we did like the inverse of a line or something like that. So sometimes those domains and ranges do work out pretty. Questions there? All right. Next question. So another inverse. So the original function was x plus 2 over x minus 1. All right, so first change your f of x to a y. Switch your x and y. And then just like on the last one, we have to solve for y here. So I can multiply by my y minus 1, get rid of the fraction. So I need everything with the y on one side and everything without it on the other. So we can subtract over this y and add over my x. What can you do here then? You could take out a y. And divide. So the inverse is 2 plus x, or you just write that as x plus 2 over x minus 1. So it just so happened that this function is equal to its own inverse. We know domain of the function is equal to the range of the inverse. So if I look at my original function, what can x not be? 1. So it's negative infinity to 1, union 1 to infinity. Range of the function equals the domain in the inverse. So again, the bottom can't be 1. Um, 26, we didn't ask about. Would you guys be prepared if I asked you to graph a function or a log, plot those? You know you have to have a minimum of 3 exact points, so we usually plugged in our -1, 0, and 1.
How would you do that for the log?
Okay, so let's say I graphed, let's do the last one. So we had j of x equals log base 1/2 of x. So this is like y equals log base 1/2 of x. So what we could do is change it to an exponential. So it is 1/2 to the y power equals x. So when you make your t-chart, what would you plug in your numbers for? The y. So 1/2 to the -1 is 2, 1/2 to the 0 is 1, and 1/2 to the first is 1/2.
And the 0 just put it in.
Yep. So you get 2, -1, 1, 0, and 1/2 1. Remember the logs have that vertical asymptote, so it looks like this. So if it's a log, you change it to an exponential, and you plug in -1, 0, and 1 for the y. Change of base, we already talked about that. You guys are good with the expanding problem on problem 28. So I'll probably ask you a couple expanding and condensing problems. Make sure on like 28 when you expand, if you have the square root of something, what power is that? 1/2, so you bring that 1/2 down in front. 29, if I condense this, we have 3 log of x minus 1 minus 4 log of x plus 3 minus the log of x plus 5 log of y. When we condense, we are only going to have one log. Where do these coefficients go? So 2 to the third. This is a fourth, this is a fifth. Anything that's positive will go on top of our fraction. So if I'm looking, this one was a positive 3 in front, so I'm going to have an x minus 1 cubed in front. This one's a positive, so my y to the fifth will be on top. Anything with a negative coefficient will go on the bottom. So we're going to have the x plus 3 to the 4th and the x on the bottom. No, you could put the x in front of that or behind it. Either way is fine. So there was a question about 14. You didn't need me to work it out. You just needed. Okay. So 14 did not work out nicely, it didn't factor, so if that ever happens, you can always use the quadratic formula to solve that. So as a refresher, that is x equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So if something doesn't factor, you can use that. I will probably try to keep them fairly nice on the test. If I were to drop any kind of hint right there. But that is always an option if they aren't nice. Okay, we went through your initial list of questions. Alright, so number 30, I asked about the domain of the log. I had put these on the section 4.4 and 4.6 homework as well. Didn't necessarily fit in that section, but we've just been mentioning it for a week and a half, 2 weeks now, every time we deal with these logs. When you have a log, your argument has to be positive. So that means the argument, the 2x plus 3, has to be greater than 0. So 2x has to be greater than -3, x has to be greater than -3/2. So that would be -3/2 to infinity. Can't equal the 3/2 because you can't do the log of 0. So anytime I ask you about the domain of a log, it's just the argument, whatever's in the parenthesis, greater than 0. Yes?
Will this test be like the last one, like it's just kind of like a study guide?
Pretty similar. I mean, I'm going to ask the same types of questions. So, you know, I'll ask an inverse, a one-to-one, domain of a log. You can expect to see all that stuff. Okay, so problem 17. So the majority of this test will probably be, you know, solving all of your logs and exponentials because we have done a ton of that. When we have an exponential like this, we had two options. First, we always tried to figure out, is there a nice way to do it? That was, can I get a common base? So what would you do?
The 8 as 2/3, then negative x, and then 4 2 squared.
So then we have 2 to the x plus 1 times power to a power you multiply. So then when you multiply these, what do you need to do with your exponents? Add them. So x plus 1 plus negative 3x is negative 2x plus 1. Then if we had the same base on each side, what did we do?
So the exponents equal to each other.
So we have negative 2x equals 1, which means x is negative 1/2. You can always check these. It's not like the log problems. If you get an answer on these, it should work as long as you didn't make a mistake anywhere. So you can expect, several common base questions on there. Like number 14, we could do a common base. Sometimes I might ask some that maybe aren't as obvious. Like if I said this, is it possible to get a common base there?
Yeah.
Yes. What would you do for the 1/7?
7 to the negative 1.
Okay. So that means x minus 1 equals negative 1, so x equals 2. No, it does not. How about 0? So that common base, as long as you catch it, saves you a lot of time. Now, sometimes you can't get a common base. So, for instance, 16. So if the common base is not an option, what do you have to do? Add a log. So on these exponentials, if you're looking at the problem and it originally has no logs in it, you're first seeing, can I get away without ever putting a log in here? Can I just change it to a common base? If not, then we add a log on each side. You can do either the common or the natural log. If one of these was like an e, if I'd said, e to the 5x equals 7 to the x plus 1, what kind of log might you want to put in? Natural log, just because the natural log and the e would drop. But otherwise, we can just do our regular one. So then your exponents come down. And then what do you have to do?
You have to get all of the things up there. But now you can shoot.
Yes. First, we have to distribute. So we have x log 5 plus 2 log 5 equals x log 7 minus 2 log 7. Then what do we have to do? We need all the x's on one side. So I'm going to subtract over this x log 7. And everything without a log on the other. So I'm going to subtract over this 2 log of 5. Then what do? We can pull out the x. For the sake of time, can I cheat right here? Don't do that on your test. Show your work. And so then you have x equals the division. I encourage you on the test, write out what you're putting in your calculator, because we remember sometimes just a missing parenthesis can really change your answer. So as long as I know what you were putting in your calculator, you won't miss very much. But if I don't know what you put in and you had the wrong answer, then I have nothing to give you credit for. So the more you show me, the better.
So you put one around the entire thing and then around one else?
Yes, every time you push the log, it opens a parenthesis, so you have to close it for all 4 of those. And then since we have multiple terms, you need one around the entire top and one around the entire bottom. Okay, so if common base isn't an option, we add logs. Let's see, how much time do we have? You guys are good with the expanding and condensing properties of your logs? Okay, so we talked about all the different exponentials. What about solving log equations? So sometimes they're nice equations. Something like, I probably tended to not put as many nice ones on the study guide. I try to make my study guides a little more challenging to make it work harder for it. But I could give you something like log base 6 of x equals 3. Then how do you solve these? Yeah. So it's just 6 to the 3rd equals x, so x is 216. I might make it, something like log base 2 of no, I don't want to do that. Let's make it log base 2 of 32 equals x plus 4. So what would you do here? If you only have a log on one side, you just change it into an exponential. Now this time I have to solve this exponential. They don't have this. As written, you could add logs, but what else could you do? 32 is 2 to the 5th. So watch for those opportunities to get a common base. Okay, they might start that way. It might be those log problems. What if?
Can you do something like 11?
Yes, I was just looking for that one actually. So problem 11. We have the natural log of 6 plus the natural log of x equals 3. So this is like the step up from the last problem. So this time I have 2 logs. Now it's not a case where everything has a log. We have to first combine those logs, but I'm not just going to drop it from each side. We'll have to change it to exponential. So these properties of logs keep coming back. If you have 2 logs added, how do you put them together? Multiply. So that is a natural log of 6x equals 3. Now it's like the previous problem. There's a log on one side. So change it to exponential. So that means e to the 3rd power equals 6x. And then you just divide by 6, and you can put that in your calculator if you want, or leave it like that. Either one is fine. So we're okay with a problem like that? What if I gave you one like problem 19? Are you okay with that, where you had 3 logs in it? So we had log of x plus the log of x minus 2 equals the log of x plus 4. So these 2 logs are added. How do you put them together? How do you take x times x minus 2? Yes, so it becomes x squared minus 2x. So then you have a log on each side, so what can we do? Drop it. So it's a quadratic, you set it equal to 0, so subtract over the x and subtract over the 4. So x squared breaks into x. What multiplies to -4 and adds to -3? So then we set each of those to 0. So we get x equals 4 and -1. On the problems that start with a log, if there's a log in the original, you do need to check that you can plug these both in. If I put in a 4, I'm good, but if I put in a -1, I am not. So 4 is the only answer we get there.
What do you mean by, you just said like if there's a log in
In the original. So like problem number 16. We added the logs into that problem,
Okay.
so we don't have to worry about it. But 18, 19, 20, when the problem starts with logs, you need to make sure and check your answers. Alright. Other questions on these? We know when we have to add logs, if we can't get a common base. Make sure you review those equations, all those different types, and know your strategies on each. Any other problems that you want me to work out? Or you want me to make up a similar problem too, if you really had trouble with something.
We're gonna get the formulas for, are we going to get the change of base formula?
No, you should know change of base, but if you needed anything like the pH or anything like that, I would give it to you.